This is Return of the Levidia, a small, open-world tactical RPG I've been developing. And lately I've been thinking about how I was going to tackle reactivity based on player actions and the world state. So, for example, opening the door to this blacksmith. Currently we can just walk in, but what if it's late at night and is locked? Maybe we need a key or a lockpicking ability. Or what if the player helped the blacksmith find love and now his wife is inside? Or maybe the player made a choice resulting in the blacksmith's death, so now it's vacant. When the world reacts to the player, it helps the game feel more responsive and alive, even if the reactions are all scripted. I was inspired by the now archived adventure game at learn.unity.com to create a system using the experimental GraphView API and scriptable objects to serialize conditions and their respective reaction sequences into various triggers in our scenes. The system, which I've been calling EventGraph, has not been used in any production capacity yet, so take all of this with a grain of salt. But I'll be integrating it into Return of the Levidia soon to see how it holds up. If I find any issues or improvements, I'll post updates in the description and on the GitHub repo linked below. Our graph is made up of 4 components. A mono behavior, which triggers our graph either on start by a player interaction, a collider, or an event subscriber. Our trigger contains the entire graph in 2 lists, an event node data list of scriptable objects, and an event edge data list. An edge simply has an output and an input ID and an output port name. Since each node will only have one input, we don't need to keep track of that. Our event node data is a generic of type event node item data and has a unique ID and a list of items. There are 2 node types, condition nodes and reaction nodes. Condition nodes have a list of event conditions, while reaction nodes have a list of event reactions, each of which we'll be inheriting from and filling out a bit later. One thing to note about this overview is the scriptable object class. Normally, we create scriptable objects as assets or sub-assets in our project. However, since we want to be referencing scene instances, we're going to be serializing them into the scene itself alongside the mono behaviors. This allows us to take advantage of their polymorphic serialization properties. As a side note, the serialized reference attribute is another way to accomplish this. However, in my experience, I've had difficulties binding custom editor properties to serialized reference fields. But if anyone who uses serialized references and knows more, please let me know in the comments, or even better, a pull request on the repo. To create the system, we're going to jump into a little scene I created. We can imagine this is the interior of a shop, and our player's goal is to steal the orange cube without getting caught by the shopkeep. This scene provides a few different paths for the player to accomplish this depending on their playstyle, but it can be difficult to code and visualize. Let's say if the player just grabs the cube, an alarm will go off, trapping the player, resulting in a game over. But if the player had previously purchased a replica and they have a high enough dexterity skill, they can swap it out. Or say the player has a high hacking ability and can hack the security system, but in order to do that, they'll have to get the shopkeeper in the back room first, which let's just say they can only do if they have knowledge of the shop inventory they got elsewhere. Or maybe if the player has a companion with them, they can con the shopkeep into giving them the cube because the companion has some intimate knowledge of the shopkeeper's guild or something. I don't know. Okay, one last thing before we finally jump into Writer and dive into code. We just need to create some assembly definitions. We'll start with getting the base event node item data classes set up, and a couple of test conditions and reactions we can use to verify things. We pass in the event trigger to help resolve any dependencies the conditions may have. The react method will return a coroutine, which we'll discuss later. This test condition will help us debug setting a pass-fail. await reaction will help us delay further reactions in our graph. Next, we'll create the base event node data and the generic node. Note, we're implementing the iSerialization callback receiver interface since we can't serialize the ID as is. Now the condition node and reaction node. We'll add our port names for easy access later. The event edge data will also serialize their IDs into strings. Okay, and finally for now we'll make the event trigger and the start trigger for testing. Now that we have the classes in place, we can start on the editor to hook things up. We only want to show the graph when we have a mono behavior with an event trigger component, so we'll listen to the selection changed event and play mode start changed. You could instead create a sidebar which would display all of the event triggers in the scene, and you could select from there, but I prefer this method as a bit more explicit which event trigger you're working on. If we don't have an event trigger selected, we'll just show a message. Since we're serializing the graph into the scene, we also cannot modify a prefab, so we should also check for the current prefab stage. Let's test all this out. Great. Now we need to display our graph in the event trigger as a root node. We'll inherit from the graph view and pass in the editor window and event trigger in the constructor. We'll also add various manipulators to control the UI and a grid background. I'd also like to mention a lot of the GraphView code comes from Mert Kiramgari's YouTube channel and his Simple Dialog Graph tutorial series. There is a link in the description below. We'll create getters for our edges and nodes. Once we've finished that, we can now add our graph view to our editor window. For our grid, we'll need to create and load a style sheet. I'll also add a few other styles for later. To create the nodes, we'll want to add a search window by implementing the iSearch window provider. We will then create an instance of each of our nodes and add it to our graph and mono behavior on selection. For our createNode method, we'll only add an input port and add it to our graph for now. We'll also set the position of our node to our local mouse position. Creating each of the condition and reaction nodes will require a drop-down to select which condition or reaction is contained within their list. We'll create a drop-down field using reflection and checking the subclass. Then, for our condition node, we'll create our condition ports. And finally, an event for when a drop-down choice is selected to add a new instance of the selected scriptable object. To create a property box, we'll add a foldout and serialize the newly created object. We'll iterate over the fields and create property fields bound to that object. And finally, we'll add a button to remove the object as well. The reaction will be pretty much the same. But now we have an issue where we aren't loading the graph, so we can't see our changes if we close it. Let's rehydrate our graph when we enable the editor, by looping over all of our nodes and creating property boxes for the existing ones. So far, we haven't been worrying about the edges. First, we'll have to override the getCompatiblePorts method of the GraphView. And then, we'll create a quick helper function to connect two nodes together. Finally, we'll listen to all changes in the graph to modify our serialized event trigger node and edge lists. The GraphView API provides us with a GraphView changed event, which has edges it will change, elements it's about to remove, and elements moved. We can use those to keep our serialized data in sync. And with that, our GraphView UI is in place. In part 2, we will create more conditions and reactions and hook them up into our scene. Thank you for watching.